Welcome back, Falcons. I hope the first parts of going through the hypothesis test, the situation, we're starting to understand this approach of phantoms. And the idea is we're looking at either to reject or fail to reject the null hypothesis. So I do want to have some words of advice before we actually do some of these questions. So do not make the null hypothesis what you hope to show to be true. It's much safer to first determine the alternate hypothesis. And based on what you think may be the results of the study, that's like the alternate hypothesis might be the one you want to show to be true. If you believe the null was in fact true, you would not be performing the study, right? I often say like the null hypothesis is like nothing to see here. You can fail to reject the null hypothesis, but you never, ever accept or prove the null hypothesis. We don't say the null hypothesis is true. We just fail to reject it. So you must check and report that you have met the necessary conditions. So we need randomization, independence, less than 10%, and a sample size that is large enough to justify the use of a normal model. Do not accept the null hypothesis. Okay, if you fail to reject the null, do not assume a larger sample would be more likely to lead to rejection. If you've done your job properly, a larger sample size should not return a different result. Remember, if we're using a normal model, a larger n, let's say n1 is bigger than n2, is just going to make it more narrow. And so it doesn't matter the larger the sample size. If we followed these techniques, our data should hold true. So just know, each sample is different, and another sample will not necessarily duplicate your current observations. If your assumptions hold, a larger sample should not lead to a different conclusion, but will increase the confidence in the decision. And that's what we're really going for. If you increase n, you're going to increase the confidence in our decision. Okay, so to put this all together, we know that confidence intervals and hypothesis tests are related in methodology and evaluating models. So a hypothesis test makes a reject or fail to reject decision about the plausibility of a parameter. This is our p-value. Our confidence interval provides a range of plausible values for our p. So we start with a null hypothesis. We also look at an alternate hypothesis. It can be one or two-sided, right? Are we looking above? Are we looking below? Or we don't know where to look, so we are going to say both. We're going to check our assumptions and conditions. If the data are out of line with our null, so that means we got a large standard deviation, a large z-score, or the p-value would be low, we're going to reject the null. If the data is consistent with our null hypothesis, which means that the chances that we get our data is rather large or a p-value is high, we're going to fail to reject the null hypothesis. And lastly, we're going to state our conclusion in context of the original question. So I do need you to include these values. We're going to include our alpha level, our p-value, our statistic, and our test statistic in your report. So in addition to all of these assumptions and conditions that must be checked, I'm going to expect you to find 4 values in every hypothesis test. So we're going to find the alpha level. So this will usually be indicated in the problem. If it's not given in the problem, the default value is 0.05. So alpha must be indicated. And that 0.05 should sound like like a 95% confidence interval. They kind of go back and forth between each other. The p-value, this is found from the data. As indicated, the p-value is the probability of obtaining the sample statistic if the model indicated by the population parameter is true. So given that our null hypothesis is true, what's the likelihood of getting the actual data? We're going to use either normal CDF or t-CDF once we get to t-statistics. We're going to indicate our critical value of our test statistic. So that is either Z star or T star. We'll get to T star in a second. And that's determined by our alpha level, as we've seen. So this is our inverse normal or inverse T. Finally, the calculated value of our test statistic, we are going to report out the Z-score which is determined by the sample statistic. Remember, z-score is our value minus the mean over the standard deviation. Only this time, it's going to be p hat minus p naught over the standard error of our null hypothesis. Okay, so if we are ready, let's do this thing. So I'm going to read the problem, and then we're going to walk through an entire example. And the only way to get good at these is to just do them over and over and over again. So a 1996 report from U.S. Consumers Product Safety Commission claimed that at least 90% of all American homes have at least one smoke detector. A city's fire department has been running a public safety campaign about smoke detectors consisting of posters, billboards, and ads on the radio and TV and in the newspaper. The city wonders if the concerted effort has raised the local level above the national 90% rate. Building inspectors visit 400 randomly selected homes and find that 376 smoke detectors work. So we're given P of 0.9, and I'm going to write P naught. We're given a sample size of 400, and X, which is N times P, is 376, which also means N times Q is 24, if I can do the math correctly. So the question is this evidence that the local rate is higher than the national rate? Is higher. And is this convincing evidence that the local rate is higher? Okay, so two questions. This is where we are coming up with our hypothesis testing. So what's the first thing that we need to do? Well, we're only interested in the increase of proportions of home with fire detectors. If the proportion is less than the US, the campaign did not have the desired result. Thus, the result will run a one-tailed test. So what I'm going to say is the null hypothesis is equal to the national average. Let's say 0.9. If you want to use P naught, you could do that same. We're just going to say the true value is 0.9. I say a one-tailed test because we want to see, did this advertising, the alternate is that it's higher. Is the proportion higher? Okay. And you know what? I'm going to be a little more difficult. Technically, the null hypothesis would be 90 or below. And I want to know, are we greater than 0.9? So I'll accept either version of this null hypothesis, but I do need to see the null where the p-value is equal to or greater than or equal to or less than or equal to some value, okay? And I also need to see the alternate hypothesis. So in this case, our alternate is our true proportion is higher than 90. So we do have a simple random sample of 400 homes. I know this because we were given that. So it's reasonable to assume homes having fire detectors is independent. Just because your neighbor has one doesn't necessarily guarantee that you have a fire detector. Sorry, a smoke detector. We know that NP and NQ, or NP hat and NQ hat, which is 376 as it should be, and 0.06 would be 24. We already saw that. NQ, 24 is definitely greater than 10. So our sample size is large enough to justify using a normal model. Now our normal model will be 0.9, comma, the standard error of our null hypothesis. And our standard error for our null hypothesis is the square root of 0.9 times 0.1 over 400. And if we go to a calculator, I'm going to say control square root. And I'm going to say control division. And I have 0.9 times 0.1 over 400. Gives me 0.015. Okay, so on our notes, you can see where this number came from. So we are testing a proportion against a known population value, and have met the conditions necessary for a one proportion Z test. Note, this is a Z test because we're doing a hypothesis test. We'll be using a probability of 0.1 as the critical level for rejection. This is what I have referred to as the alpha level. Now, how did we know that we were looking at that as our alpha level? I'm giving it to you. So in this case, I'm giving you the alpha level is 0.1. So calculate the test statistics as always, even if you do not use the calculate, use it. We are going to calculate Z. I know it seems ridiculous, but this is one of the things that in order to justify using the technology, we need to come up with the test statistic, which is our Z-score. So to find Z-scores, it's p hat minus our null hypothesis divided by 0.015, which is what we found. So I have 0.94, which is the measured rate, which was 376 over 400, minus 0.9, which is the null hypothesis over its standard error, and we get 2.6667. So this is our test statistic. So to find the p-value, what we're looking for is what's the probability of getting a z-score that's greater than 2.6667. What are the chances that I get a z-score higher than that? Well, we know how to do that. If I know what my z-score is, I go Menu, Statistics, Distributions, Normal CDF, and my lower bound is 2.6667. My upper bound is 999, 0 and 1. And I get a p-value of 0.0038. Or what I'm asking you is, what's the probability that I get a sample percentage of 94%? So I could do a normal model again, normal CDF, 0.94 to a really large number, 0.9 comma its standard error. So I get a p-value again, which is 0.0038. So as always, what is this actually saying? If I'm centered at 0.9 and I went out and I saw that 376 out of the 400 homes had smoke detectors, what percent of the time would I get that or higher? Well, that's 0.003 or 0.38% of the time. Well, is that statistically significant? You can also see why instead of having to go 1, 2, and 3 standard deviations, it's far easier to just use that standard normal model, 0, 1, 2, and 3, and then compare it to my z-score. So have I gone to my calculator yet? No. So when I go to my calculator and do this, I'm going to Menu, Statistics. Now I'm going to go to Tests, and I'm going to do a one prop Z test. So my null was 0.9. The number of successes was 376. My sample size was 400. And my alternate hypothesis was I was greater. And I'm going to hit equals. Note what the calculator gives you. I get my z-score. So as long as you give me the setup for it, you can jump here. I get my p-value. Again, as long as you give me the setup, you can jump here. I have my p hat, which is 0.94, and my n, which is 400. So this is everything I need from the calculator side. So finally, we're on the M part of make your decision. So the probability of obtaining a z-score of 2.667 or greater is 0.0038. Note, this is your p-value. And since 0.0038 is less than 0.1 or 10%, it is unlikely we would obtain a proportion of 0.94, since by simple chance or sampling error. So what does that mean? If we're below alpha, or our p-value is less than our alpha value, we are going to reject the null hypothesis. And then finally, we're going to state our conclusion. So we would expect to get a proportion of 0.94 in only 0.38% of sample sizes of 400. That probability is small enough for us to conclude that it is likely, notice, squishy word again, it is likely the promotional campaign did increase smoke detector use. Okay, so since we rejected the null, since we reject the null hypothesis, I want to build a 90% confidence interval to say, well, where would the true population proportion of homeowners with smoke detectors be? So again, we've already met the conditions for creating a confidence interval. And since they're the same from our hypothesis test, we have satisfied the conditions for a 1 proportion z interval. So again, we need to find a new standard error because this time we're looking at p hat as our middle, not our null hypothesis because we rejected it. So we're going to do 0.94 times 0.06 over 400, take the square root. Then we get our standard error for our sample proportion. Now, because we're doing a 90% confidence interval, I want to get my critical value, or my z star, just as a reminder on my calculator to get my z star, or my critical value. I go Menu, Statistics, Distributions, Inverse Normal, and because it's 95% or 90%, I go 0.9501. I get 1.645. 6449, we're going to use that. So my true population proportion will be 0.94 minus z star times the standard error of our sample proportion, remember, or it will be above that z star standard error of our sample proportion. And this is our p hat. So how do we do this on our calculator? We're going to go to Menu, Statistics. We're building a confidence interval. We're doing a 1 prop z interval. The number of successes still stays the same, 376, 400, and we are at a 90% confidence interval. So the calculator tells us that the lower is 0.9205. The upper is 0.9595. Okay, back to our screen. We are 90% confident that the actual proportion of homes in this city using smoke detectors is between 92.04% and 95.96%. Or our critical value, confidence interval at 90%. That's pretty cool. That's a lot of work to be able to do this test. We're going to do a couple more in class. Now, of course, as I showed you along the way, you should have started with the calculator, right? Once you get the calculator stuff out of the way, as we've shown, so if you're on your TI-84, which I know some of you are, we're going to go stats, tests, and then go down to number 5, which is a 1 prop z test. P hat is 0.9. Our success is 376, 400, and then we're greater than our null hypothesis. So this gives me my test statistic, which is my z-score, my probability or p-value, test statistic. P-value, our sample proportion, and our sample size. Okay. Let us pretend for a moment we had no idea which way the results would go. We would then have to do a two-tailed test. So all the calculations are going to remain the same. The only change is the p-value. And I want you to think, if we're doing two-tailed test instead of a one-tailed test, we're equally as likely to be above or below. So our p-value is going to just double. The only reason we found our positive value is due to chance, right? So now run the test with not equals. So on your calculator, just because we can, one more time, I'm going to get Menu, Statistics. We're going to go to a test, and we're going to do a 1 prop z test. Our null hypothesis was that we're at 90%, 376, 400, and we're just going to say we're not equal to it. And you can see that our p-value is 0.007661. So if we didn't know anything, we're still underneath our alpha level of 0.1 by a significant portion. So this is statistically significant evidence that our ad campaign may have worked.